Hello viewers, so in this video we're going to learn how to derive the Henderson-Hasselbalch equation for a weak acid. Now this is a formula that is used to find the pH of a buffer solution. So let's go ahead and see how we can derive it. So the first step is to use an acid dissociation. So we're not going to use an actual acid, we're going to use the acid specimen. So the specimen we're going to use is HA, where the H that we have here, the H that we have here is the acidic hydrogen that makes the whole substance an acid. So that's the specimen we're going to use. All right, so let's go ahead. So the first step is to put it in water. So we're going to put the acid in water. And when we put this acid in water, what we are going to produce on the other side is we'll have the hydronium ion and the conjugate base will be produced. So this is what we produce when we add this acid in water. In case you are wondering how we are coming up with the products, what is happening is whenever you put an acid in water, water is acting as a base. So since an acid is a proton donor and the base is a proton receiver, the acid is going to donate a hydrogen to water. When it does, this is why we are producing the H3O plus ions. And what remains here is what is produced on the other side. We can see we have it as a conjugate base there. So this is our dissociation equation for this acid. The next step is to write its Ka expression. So the Ka expression is equal to, we have the concentration of the hydronium ion, that is multiplying by the concentration of the conjugate base there, and this will divide by the concentration of the acid down there. If you are wondering why we are not including water, water is in liquid form. So anything that is in liquid form or solid form is not included. So water is in liquid form, therefore it's not included. Now, the formula we're calculating is for finding pH of a buffer solution. Whenever we're talking about pH, our main concern is the hydronium ion. So we're going to make the hydronium ion the subject of this formula here. So let's do that. When you cross multiply, what we'll get is we'll have our Ka multiplying by the acid concentration that we have there. And this whole thing will be equal to, on the other side, we still have the hydronium ion concentration multiplied by the concentration of the conjugate base. Since we are making it the subject, we're going to divide by the concentration of the conjugate base. So that's what we have there, and we are also dividing on this side here. When we do that, you're going to find out that this concentration and this concentration will cancel. What we'll have on the other side, we'll have the hydronium ion concentration like that on one side alone, meaning we've made it the subject. This will be equal to, on the other side, we have Ka, that is multiplying by the concentration of the acid, and the whole expression is divided by the concentration of the base, like that. All right. So what we have there can be rewritten in this format where we are saying we'll have the hydronium ion concentration here. This is equal to, now we can write it as Ka multiplying by the acid concentration here, that is divided by the base concentration that we have there. So what we have here, Ka multiplied by this ratio, is the same as Ka multiplying by that and dividing by this, to the same thing that we have here. We've just rearranged it in this format. So this is what we are going to use now. From there, our next step is to introduce negative log on each side. So we introduce it on the left side and also on the right side. So we'll say negative log of the hydronium ions concentration here is equal to negative log of, we have our Ka multiplying by still the ratio that we have there. Yes, so this is what we have. We've introduced our negative log on the left side and also on the right side. All right, so let's go ahead and see what comes next. What we have on the right side here, if we remember our logs very well, we understand to say if we have log xy, log xy is the same as log of x added to log of y. So this is the same. Log xy is the same as log of x added to log of y. If you look at this side here, what we have is negative log of Ka multiplied by that ratio there. So this is the same concept we have here. Log of x multiplied by y can be written in this format. Even this can also take the same format. So let's do that. So we have on this side, we still have negative log of the hydronium ion concentration like that. And this is equal to, on this side, we'll now say we have negative log of Ka, and this must be added to negative log of the ratio that we have there, which is the acid concentration divided by the basic concentration or the concentration of the base. Now we'll put this in brackets. All right, so negative log of H3O plus on the left side here is equal to negative log of Ka, and this, when we multiply negative by positive here, we're going to get a negative. So we'll say this will be minus log of the ratio that we have on the other side. So this is what we have now. This is what we have now. So negative log of Ka minus log of the ratio that we have, which is the concentration of the acid divided by the concentration of the base. All right. So if we remember again, we understand to say negative log of the hydronium ions concentration is equal to pH. We not say we can find pH by getting the negative log of the hydronium ion concentration. We also remember that negative log of Ka is equal to pKa. Yes, we can get pKa by just taking the negative log of the Ka value. So this is what we have there. Now, we should also remember our logs to say if you have, for example, let's say you have negative log of x divided by y. This is the same as log, let's put it like that. This is the same as log of y divided by x, like that. If you have negative log of xy, this is the same as log of yx. So we are going to apply this concept we have here. Negative log of x over y is the same as log of y over x. So this is what we are going to apply here. Negative log of HA concentration over A minus concentration is the same as log of A minus concentration over that concentration. So let's do that. Let me put it here so that you can see it from here. All right, so what we have is we are going to have negative log of HA concentration divided by A minus concentration. This is the same as log of A minus concentration divided by HA concentration. Yeah, so that's what we have. Now, what we are going to do to just finish up our derivation or driving, we are going to now replace with what we have. Remember, negative log of the hydronium ion concentration is equal to pH. So whenever we have this in our formula there, we're going to replace with pH. Negative log of Ka is equal to pKa. So we're going to replace negative log of Ka with pKa. And where we have the negative log of the ratio, we're going to replace it with log of that ratio. So let's do that. Meaning negative log of hydronium ion concentration on the left side will be replaced by pH. This is equal to negative log of Ka is replaced by pKa, and negative log of the concentration of the um, acid divided by the concentration of the base is replaced by log, which is the positive log of, on top there now, we are going to have A minus concentration, like that, divided by, now down we have HA concentration. So this is the formula we're basically deriving, and this is the Henderson-Hasselbalch equation for a weak acid. So pH is equal to pKa added to log of the base on top, and then we have the acid down here. This can be rewritten in this format. This is the same as pH is equal to pKa. Then we added to, on top there, this is log, on top there we have the conjugate, that's base. So conjugate base concentration, we're talking about the concentration of the conjugate base divided by the weak acid. So weak acid down here, concentration as well. So this is the Henderson-Hasselbalch equation, and this is how you drive it.